This is the lecture in which we will visualize the following function. R of x equals the pair of functions cosine of x, comma 2 sine of x. As you can see, when you fix a real number and you apply r to it, you get a pair of real numbers. Therefore, this is a function that goes from the set of real numbers r to the set of pairs of real numbers r squared. Here is the situation graphically. We have the domain here on the left, which is represented by this green line, and we have the codomain of r on the right. As we just said, the codomain is r squared. Therefore, we represent r squared as a Cartesian plane with two orthogonal axes, which will help us to display two-dimensional vectors. As usual, we represent the image of a random point in the domain. In this case, it's the number 2.87. We call it P, as we have done in the previous videos. Now, applying r to p, of course, we will be getting a pair of real numbers. The function that is given by cosine of x, comma 2 times sine of x will give as image the pair of numbers negative 0.96 and comma 0.54. And the image is represented in the Cartesian plane by this purple dot. Now the function I that goes from the domain to the graph applied to P by definition is the pair given by, as a first entry, we have the point P itself in the domain, and the second entry is the image of P. Explicitly, P is a real number, so it's 2.87 in this case, whereas r of p is a pair of real numbers. The image of p is a pair of real numbers. We write them after the first coefficient as negative 0.96, comma 0.54. This gives us a triple of real numbers, therefore an element of R3, the three-dimensional Cartesian product of the real line. And this shows us that the graph of this function r will live in R3. Let's see now the image of a few more points in the domain, about 20 of them, and see if we can say something about the function r in this case. We have seen in the previous videos that the image really, for the function f and g, didn't really tell us anything about the function. Let's see in this case if we can gather more information. Okay, we see here that the points in the domain tend to go in a structured way in the codomain. They don't seem to go randomly spread out in the plane, but they actually seem to sit on some curve, some sort of curve. Let's go a little further. Okay, now we have the image of about 1,000 of points, and we see that they all end up in this ellipse centered in the origin. Therefore, this is going to be the image of R. So the image of R in this case already tells a lot about the function r, because it says that every single point in the domain will be taken to some point of this ellipse, and this is non-trivial information about r. Let us now construct the setup in which we will be able to draw the graph of r. As we have seen, the graph of r belongs to the space given by the Cartesian product of the domain times the codomain. The domain is R, the real numbers. The codomain is r squared, the Cartesian product of the real numbers by itself. Therefore, the graph will live in R3, which is the three-dimensional Euclidean space. Now, there are several ways of representing R3s with three orthogonal lines as a coordinate system. Usually, what we do is the first two factors describe the horizontal plane, and the third factor is represented by the z-axis, the vertical line. Let's try to keep these convention valid even in this case. Therefore, since the domain is going to be the first of the three factors of R3, we will have to place it in the horizontal plane. However, in the plane that we are seeing here represents the codomain. Therefore, is generated by the second and the third factors of the Cartesian product. Therefore, the construction is slightly different from the one of the previous function, the function g, that also had the graph embedded in a three-dimensional Euclidean space. So in this case, the construction is as follows. So we change point of view, and then, okay, so we placed now the domain axis horizontally, and we keep the plane for the second and the third factor, so as a codomain. But in this case, it will not be horizontal, but it will be vertical, because the plane that we have drawn regards the codomains, the second and the third factors. Let's change the point of view. We are facing the codomain, and the domain is pointing towards us. Now let's draw the graph in this three-dimensional coordinate system by picking up about 4,000 random elements of it and see if we can guess the general shape of this figure. This is the graph represented by about 4,000 random points. As we can see, each of these points in a sense lies above the image. Okay, it does contain more information than the image itself, because the image is just an ellipse, and this figure is more complicated than ellipse, especially towards the direction of the domain. However, this is one of the few cases in which showing the image of the function tells a lot about the function itself. What are the relations between domain, codomain, and graph by representing the maps I and Q that factor the map R. The point P that we described before in the domain, represented by the number 2.87, it does have an associate point in the graph. So I of P, this yellow dot is I of P, and it is constructed exactly like in the definition of the map I. So it has three coordinates, as we have shown a few minutes ago, the first one being 2.87, and the second two are the coordinates of the image of P through the map R, namely negative 0.96 and 0.54. So an alternative way of seeing this construction is the following. We assume to have a plane that is parallel to the codomain, but passing through the point P. In that plane, Cartesian plane, we draw the point given by the coordinates of the image of P. So negative 0.96 and 0.54. This is going to be precisely the element in the graph associated to P through the map I. Let's see now the map I acting on about 300 points of the domain. Okay, so I goes from the domain to the graph and takes a point and sends it to the point that we described before. This is the geometrical representation of I, where the ending of the arrows represent the images of the points in the domain. Likewise, we have the representation of the map Q that goes from the graph to the codomain. Starting point are these yellow dots, and the arrows all end up in the image, the purple curve, the purple ellipse. The images of each yellow dot is the end of the arrow, starting from the yellow dot itself and ending in the purple curve. This is the representation of the map Q.